Hi, in this lecture we will see matrix addition and subtraction. In the last lecture we have seen what matrices are, how do we denote matrices, what is the dimension of a matrix, which is also the order of a matrix, and we have seen different types of matrices. Now we will do some operations on these matrices and we will start with adding two matrices and subtracting two matrices. So when can we add them, when can we subtract them? And we will also see one more property, scalar multiplication. So how does scalar multiplication work? So we'll see all sorts of things in this lecture. So let's start. So firstly, matrix addition. Essentially what do we want to do? We want to add two matrices, okay? But we cannot add any type of matrices, okay? So there is some criteria. Only if that criteria fulfills in two matrices, then only we can add those matrices. So the addition criteria is two matrices can be added only if they have the same dimension, only if they have the same dimensions. What is dimension? Dimension is order, right? Dimension is order, which means number of rows and number of columns. So we can only add two matrices if they have same dimension, okay? Which means the number of rows is also same and the number of columns in both matrices is also same. Both values should match, okay? Then only two matrices can be added and also they will be subtracted. Like we will see later that for subtraction also the same criteria is there. So what is the method? How do we add two matrices? Let's say we have a matrix M cross N. It can be a rectangular matrix, it can be a square matrix, it doesn't matter. For any matrix M cross N, which means it has M rows and N columns, and it is denoted by Aij, which means the element at ith row and jth column is denoted by Aij. Okay, this is the standard matrix notation. We have seen this in the last lecture. And we have another matrix B of the same order. Notice that the order is same. You cannot add two matrices which have different order. Okay, if the number of rows or column in the two matrices are different, you cannot add them. So B also has the same order and the ith row and jth element, jth column element in the matrix B is denoted by Bij. Then A plus B will also have the same order M cross N. Okay, when you add these two matrices, that also will have the same order M cross N, and the element at ith row and jth column will be denoted by Aij plus Bij. So we will just add them element wise, very simple. Okay, so let's take an example. Let's say we have a matrix A like this 2, 3, 5, 7. Okay, it is a 2 cross 2 matrix, and we have a matrix B. It is again a 2 cross 2 matrix. Let's say -3, 5, 2 and 6. Okay. Then if I want to compute A plus B, firstly I can compute A plus B. A plus B is another matrix. Okay, A plus B is another matrix, you can call it C also, but A plus B is another matrix, and A plus B will also have an order of 2 cross 2, and you can only compute if compute this addition if the order of A and B are same. So here order of A and B both are 2 cross 2, and hence we can add them, and addition will be very simple. You just have to add all elements pair wise, like element by element wise. So for the element in the first row and first column here will be added to the element in the first row and first column here. So 2 and minus 3 will be added, we will get -1. So this element will become -1, and here 3 plus 2 will become 5, 5 plus 5 will become 10, and 7 plus 6 will become 13. So this is how we can add two matrices, okay? Again, their order must be same. If let's say A is 2 cross 2, the same matrix, 2, 3, 5 and 7, and now let's say B is 1 cross 2, let's say just -3 and 2. This is a 1 cross 2 matrix, 1 row and 2 columns. These matrices cannot be added. Okay, these matrices cannot be added. A plus B is not defined, you cannot compute it. Okay, in this case. But here we can add them if the order is same. So very simple rule. In the addition, the ijth element is denoted by Aij plus Bij. So let's see some more examples on this. Here we have another example. A is a matrix given and B is a matrix given. So firstly, what is the order of these two matrices? This matrix has 2 rows and 3 columns. So it is a 2 cross 3 matrix. And this matrix has again 2 rows and 3 columns. So this is also a 2 cross 3 matrix. So we can add A and B because they have same order. Okay. And A plus B again will be another 2 cross 3 matrix, and you just have to add the elements pairwise, element by element. So the 1 and 6 will be added, here you will get 7, 0 and minus 5 will be added, here you will get minus 5, 2 and 9 will be added, here you will get 11. Or let me write it completely for your notes. So let's write the addition element by element. So here this element will become 1 plus 6, this element will become 0 plus minus 5, this element will become 2 plus 9, this element will become 3 plus minus 3, this element will become 1 plus 4, and this element will become minus 1 plus 5. Okay. So the matrix essentially will become 7 and then minus 5, then 11, then 0, then 4 plus 5, 1 is 5, and then minus 1 plus 5 is 4. So this is the final matrix. This is the matrix A plus B. You just have to add the elements element by element, which means the same element here will be added with the same I, jth element here, and you will get another matrix. This is how you add two matrices. Now let's look at subtraction of two matrices A minus B. So again subtraction has the same criteria as addition. So two matrices can be subtracted only if they have the same dimension or the same order, or if the number of rows is same and also the number of columns is same. Everything should be same. The order essentially should be entirely same. Okay. And how do we subtract two matrices? Let's say matrix A is of dimension m cross n and the ijth element is aij, and matrix B is again m cross n and the ijth element is bij. Then A minus B will again be of order m cross n, and the ijth element will be denoted by aij minus bij. Okay. So we will again subtract it element wise. But here you have to note that if you are doing A minus B, then you have to subtract the element in the A matrix, and then from that element you have to subtract the element in the B matrix. A minus B, it is not B minus A. In addition it does not matter, A plus B is same as B plus A, we know that, right? But in subtraction A minus B will be different from B minus A. So the whatever matrix is coming first, you have to take the element of that matrix first and then subtract the element of the second matrix from it, okay, like this. So again let's take an example of it. Here we have a matrix A which is of order 2 cross 3, 2 rows and 3 columns. Okay. Matrix B, again it has an order of 2 cross 3, 2 rows and 3 columns here, and that is why we can subtract them, okay, because their order is same. A minus B will also have order of 2 cross 3, so it will have 2 rows and 3 columns. So the first element will be denoted by, so we will firstly take the element from A minus the element, the corresponding element in the second matrix. So it will become 1 minus 6, and the second element will become 0 minus minus 5. So it will be 0 minus minus 5. Then you will have 2 minus 9. Then this element will become 3 minus minus 3. Then this element will become 1 minus 4. And then you will have minus 1 minus 5. So you just have to compute these things and you will get 1 minus 6 is minus 5. 0 minus minus 5 means 0 plus 5, which means it will become plus 5. Then 2 minus 9 will become minus 7. Then 3 minus minus 3 means 3 plus 3, which is 6. And then we have 1 minus 4 is minus 3. And then minus 1 minus 5 is minus 6. So this is the matrix A minus B. Okay, this is how we subtract two matrices. Now in the same example, if we had to compute B minus A, let's say if I have to compute B minus A, then that is also possible because B and A have same order, but here the elements will be different. What will be the elements? The elements will be, first we will take the element of B and then we will subtract the element of A from it. So 6 minus 1, so this will become 5. Then we will have minus 5 minus 0, minus 5 minus 0, which means minus 5. Then we will have 9 minus 2, which is 7. Then we will have minus 3 minus 3, which is minus 6. Then we will have 4 minus 1, which is 3, and 5 minus 1, which is 5 plus 1, which is 6. Okay. So this will be the matrix B minus A. Notice that B minus A is a different matrix than A minus B. Okay. All the elements have a minus sign. Here if you have minus 5, here, there you have plus 5. Here you have, if you have plus 5, there you have minus 5. Here if you have minus 7, there you have plus 7. So all the elements are of opposite sign. So A minus B will be different from B minus A. We will see this property, okay. So this property is called commutative and subtraction is not commutative. Okay, we will see this property. So always notice like which matrix is coming first, and according to that you have to do the subtraction. Again, if A and B order is different, let's say B here had an order of 1 cross 1, just a single element 5. Okay, then since A and B have different order, you cannot compute subtraction or even addition. So the criteria should match. You can add or subtract matrices only if their order is same. Okay, now let's look at scalar multiplication. So we can multiply a matrix by a scalar. We can multiply a matrix by a scalar. In the last lecture, we have seen what a scalar is, right? A single value. A single value is called a scalar. And we can multiply a scalar with a matrix, and that is very simple. So here we don't have any criteria. You can actually multiply any scalar to any matrix of any order. There is no criteria. Any matrix of any order can be multiplied with any scalar or a single value. So multiply every element of a matrix by a scalar. Essentially, how do we multiply a scalar with a matrix? We just multiply every element of the matrix by that particular scalar. So let's say if you have a matrix A of order m cross n, where ijth element is aij, and C is a scalar, and C is a scalar given, okay. C is a scalar given. Then we can multiply the entire matrix by C, and we denote it by CA, C times A, which means we are multiplying C with the matrix A. Then CA will be another matrix, and it will also have the order m cross n. It will also have order m cross n, and its ijth element will be denoted by C times Aij, which means all the elements in the matrix will be multiplied by C, that's all. So let me give you an example. It's pretty simple. Let's say we have let's say matrix A of cardinality 2 cross 2, which means of order 2 cross 2, and we have like let's say element 1, 3, minus 2 and 0. Okay, and we want to compute let's say 4 times A. 4 times A, you can denote it like this, 4 dot A, or you can also write 4A, which means you are just multiplying the entire matrix A by the value 4. Here 4 is the scalar, here 4 is the scalar C. Okay, so you just have to do what you have to do, you have to just multiply entire matrix, you can write it like this as well, like 4 times the entire matrix 1, 3, minus 2, 0, which is nothing but multiplying every element by 4. So it will be a matrix containing the first element is 4 times 1, then the second element will be 4 times minus 2. So every element will be multiplied by 4, that's all. 4 times 3 and 4 times 0. So it will just become 4 minus 8, then 12 and then 0. Okay, this is how you multiply scalars with matrices. Every element will be multiplied by the same value. This is what the matrix 4A is. If A is this matrix, 4A is that matrix. And you can also compute let's say 0 times A, then every element will be multiplied by 0, so it will just become 0, 0, 0, 0. Remember that any constant or any scalar times a matrix will be of the same order as the original matrix. Let's say if the original matrix B is of order 2 cross 1, 2 rows and 1 column, let's say 1 and minus 1, okay, and if we multiply this particular matrix by a scalar, let's say 3, then 3 times B will become what? 3 and minus 3. So the order will remain same. So 3b is nothing but 3b is also of order 2 cross 1. Okay. So this is how you multiply a scalar with a matrix. Cool. So this is what the theory is, and I hope everyone understands this part because the ijth element is now nothing but C times Aij. Okay. So let's see more examples. Here we have a matrix A, and we have to compute the matrix 3A, which means we have to multiply 3 with this matrix. So every element will be multiplied by 3. It will just become 3 into 1. This element is 3 into 3. This element is 3 into 0. this element is 3 into 1, this element is 3 into 2, this element is 3 into minus 1. Okay. So at the end the matrix will become 3 into 1 is 3, 3 into 0 is 0, 3 into 2 is 6, 3 into 3 is 9, then 3 into 1 is 3 and 3 into minus 1 is minus 3. So this is what the final matrix will be. And notice that the final matrix also has the same order. This matrix was 2 cross 3 and the final matrix is also 2 cross 3. Here again we have a matrix B. This is also a 2 cross 3 matrix, which means 2 rows and 3 columns, and we have to multiply it by minus 5. You have to multiply this matrix by minus 5, which means every element will be multiplied by minus 5. So 6 times minus 5 is minus 30, minus 5 times minus 5 is plus 25, 9 times minus 5 is minus 45, then minus 3 times minus 5 is plus 15, then minus 5 times 4 is minus 20, and minus 5 times 5 is minus 25. So this is how you can compute. Even the constant or the scalar can be negative as well. It can be 0, positive, negative, anything, and you can just multiply all the elements element wise and you can get the final multiplication. This is how we do scalar multiplication on matrices. Okay, now let's see some algebraic properties of properties of addition, subtraction and scalar multiplication. So firstly we have some properties of addition. So addition is commutative. This property is called commutative, which means on any binary things like or any binary matrices, like why am I calling binary? Because addition is a binary operator. It adds two matrices at once, right? You cannot add three matrices at once. Generally we don't do that. If you want to add three matrices, you can do that, but firstly you will add two of them and then you will add the third of them in the addition, right? So when we are adding two matrices, the order doesn't matter. When we are adding matrices, the order doesn't matter. You can do A plus B or B plus A, the answer will be same, right? Because addition works that way, right? Even for any two numbers A and B, A plus B is equal to B plus A, right? 3 plus 5 is equal to 5 plus 3, we know that. And that is why in matrix addition also we are doing the same thing. In matrices what we are doing, if we have two matrices A plus B, element by element it will be Aij plus Bij, right? If A has an element Aij and B has an element Bij, their order must be same, then only we can add, and the element is Aij plus Bij. And similarly if we are adding B with A, B plus A, then we will be doing Bij plus Aij as the ijth element. So every ijth element will be here and here, they will be same, because Aij plus Bij will be equal to Bij plus Aij, and hence when we add two matrices the order doesn't matter. Matrix addition is commutative. This property is called commutative. Next is associative. So A plus B plus C will be equal to A plus B plus C. So when we are adding three matrices, again the order doesn't matter, right? We can add A and B first, or we can add B and C first. We can even add A and C first. The order will never matter. In addition, you can add them in any order, okay? So why is it so? Again, simple thing. Let's try to prove this. So what do we want to do? A plus B plus C. So let's say A has an order m cross n. Then B also must have an order m cross n. Then only you can add A and B. And if you are adding A and B, A plus B will also have order m cross n. And if you want to add that matrix to C, C also must have an order m cross n. So you can add three matrices only if all of them have the same order. If any one of them have a different order, you cannot add them. That is one thing. Now let's say we are performing A plus B plus C in this way. So here what will happen? Firstly we are computing A plus B. So A plus B will also be an m cross n matrix whose ijth element will be Aij plus Bij, right? Ijth element will be Aij plus Bij. And now we are adding the matrix C to it. So the ijth element of this matrix is Aij plus Bij, and ijth element of C is, let's say, Cij. Then in the addition the ijth element will become Aij plus Bij plus Cij, right? It will be just the addition of all three of them. And similarly when we are doing, let's say if we do B plus C first, then also same thing will happen. The ijth element of B plus C will be it will also be an m cross n matrix. It will be Bij plus Cij. It will also be an m cross n matrix. And now we are adding A to it. A is also an m cross n matrix. So the final ijth element will be Aij plus Dij plus Cij. And these two values are same. And hence this property is called associativity. If we are adding 3 matrices, the order doesn't matter, we can add them in any order. You can add A and B first and then add C, or you can add B plus C first and then A to it, add A to it. And hence matrix addition is associative. It is commutative and it is associative. Okay. Next is additive identity. So 0 matrix is said to be the additive identity of any matrix. 0 matrix is said to be the additive identity of any matrix. But 0 matrix of what order? See, what is a 0 matrix? Any matrix with all elements 0. Any matrix with all elements 0 is called a 0 matrix. And let's say for a matrix A, which is of order m cross n, you cannot add any 0 matrix to it. You can only add the 0 matrix which is of size m cross n. Its order must also be m cross n. So 0 matrix can have any order, right? All elements are 0. And only you can add the 0 matrix of order m cross n to a matrix of size m cross n. And the property is, if you add 0 matrix to any matrix, you will get the same matrix again. You will get the same matrix again, right? Because we are just adding 0 to all the numbers. So we will get the same matrix again. And this property is called additive identity, which means 0 matrix is called the additive identity of any matrix. Because if you add that to any matrix, you will get the same matrix again. This is called additive identity. Later we will see multiplicative identity as well. What number should I multiply such that I get the same matrix back, right? So the additive identity means what you should add to a matrix such that you get the same matrix. So that is a 0 matrix of size m cross n. This is not the number 0. This is not the number 0. It is the 0 matrix of size m cross n. Okay. So 0 matrix of order m cross n is the additive identity, of any matrix A of size m cross n. Okay. The reason is very simple. If you have any matrix A, let's say of size 2 cross 2, let's say elements are 2, 3, minus 1 and 5, and to the matrix A which is of size 2 cross 2, if you add the 0 matrix of size 2 cross 2, it is nothing but you are doing 2 minus 1, 3, 5 plus 0, 0, 0, 0. 0 matrix of size 0, 0 of size 2 cross 2 is 0, 0, 0, 0. So you will get the same matrix back, which is A. 2 minus 1, 3, 5, which is the same matrix A. And that is why 0 matrix is called the additive identity of any matrix, but it should be of the same order. Okay. So these are some of the properties of addition. Now let's look at some properties of subtraction. So subtraction is not commutative. Subtraction is not commutative. Again, for normal numbers also, we have already seen this, right? When you are subtracting matrices, A minus B will not be equal to B minus A. We have already seen examples as well. Actually, they will not be same, right? We saw the example in previous slides when we saw subtraction. Yes, here A minus B was this matrix and B minus A was this matrix. They are different. Actually, every element is different, right? Like the sign is different. If here we have minus 5, here we have plus 5, and hence they are not the same. Two matrices are considered to be equal or same if all the elements are same. Even if one element is different, the matrices are considered to be unequal. Okay. So A plus B and A minus B and B minus A are different matrices. They need not be same, and hence matrix subtraction is not commutative. It is non-commutative. We call this property non-commutative. And the reason is very simple. I think like everyone understands, because here the ijth element will be Aij minus Bij, and here the ijth element will be Bij minus Aij. and these two values need not be equal in math, right? For any two numbers you cannot say that these two values are equal. They will be equal only if like both are 0, right? So essentially, or if the subtraction is 0, essentially only if the subtraction is 0. So yes, two matrices, if you are subtracting them, it is not commutative. It is very important to note. You have to see, like whenever you are subtracting, you have to see which matrix is coming first, and hence the result can be different. And similarly, matrix subtraction is not associative also. It is not associative, because if you are performing, let's say, A minus B minus C, then like order matters, right? Like if you are doing A minus B first and then minus C, here the ijth element will become Aij minus Bij. Aij minus Bij will be the ijth element of this, and you are subtracting the Cij from it. So the ijth element will be this much. And if you are doing A minus B minus C, if you are doing this first, then the ijth element of B minus C will be Bij minus Cij, right? And you are subtracting Aij minus this thing. So the ijth element will become Aij minus this entire thing, which is Bij minus Cij, and hence this will become Aij minus Bij plus Cij. So this value is different from this value, right? Here we have minus Cij and here we have plus Cij. So you cannot just put brackets anywhere, okay? It depends. So whenever you are subtracting three matrices, you have to tell like which matrices you have to subtract first and then which matrices, okay? Otherwise the result can be different, and hence matrix, these two values are not equal, and hence matrix subtraction is not commutative and it is not associative as well, okay? But what properties hold? Additive inverse, additive inverse. So like if you subtract a matrix from itself, you will get the 0 matrix, right? It's very obvious thing. So for any matrix A, if you subtract A from itself, so you will get the 0 matrix. If A is of order m cross n, and if you want to subtract a matrix, it also has to be of order m cross n. And if you are subtracting a matrix from itself, you will get the 0 matrix of size m cross n. The reason is very simple. Let's say the ijth element of A is Aij and ijth element of A will again be Aij. So the ijth element of A minus A will become Aij minus Aij, which means you will get 0. You will get 0 in all the m cross n rows. You will get 0 in all the m cross n rows, which means all the elements will be 0, which is just a 0 matrix of size m cross n. And that is why minus A is called the additive inverse of A. Additive inverse means what? Additive identity is different and additive inverse is different. Additive identity means what do I add so that I get the same matrix back. So additive identity is the 0 matrix, but additive inverse means what do I add so that I get the 0 matrix. So additive inverse for any matrix A is minus A, because if you add minus A to any matrix A, you will get 0, or you can write it like this also. If you subtract the same matrix from itself, you will get the 0. Both these things are same. So minus A is called the additive inverse of the matrix A. Minus A is also a matrix of size m cross n. A is also a matrix of size m cross n. Now you can ask, what is minus A? Minus A is nothing but minus 1 into A. We already know what scalar multiplication is, right? So minus A is nothing but minus 1 into A. So you are just multiplying the entire matrix with the scalar minus 1. So you can perform this multiplication as well. So let's say the matrix A is 2 cross 3 matrix. It is 2, minus 3, 0, 5, 7 and 1, okay. So the matrix minus A will be nothing but minus 1 into A. So every element is multiplied by minus 1. So you will get minus 2, 3, 0, minus 5, minus 7 and minus 1. We already know that if you just directly perform subtraction, which means if you do A minus A, you will just like subtract the same matrix from itself, you will get 0 matrix. We already know this thing. And also if you add these two, which means if you add a and minus a, also the same thing will happen, right? A plus minus a is nothing but a minus a, they are same. So again, if you add these elements, element by element, 2 minus 2 is 0, minus 3 plus 3 is 0, 0 plus 0 is 0, 5 minus 5 is 0, 0, 0. And hence minus a is called the additive inverse of a. Okay. So this is how additive inverses work in matrix addition and subtraction. Okay. Now let's see some properties of scalar multiplication. So scalar multiplication is distributive over addition. It means that if you have a scalar multiplication of addition of two matrices, then you can just distribute it over the two matrices and then you can do the addition. Okay. So this is this property is called distributiveness. Like in numbers also we see this, right? Let's say we have a number a and you want to multiply it with b plus c. You can actually write it as ab plus ac. So we can say that multiplication is actually distributive over addition. You can distribute multiplication over addition. Same thing happens with matrices as well. If you are multiplying by a scalar, and you are multiplying a scalar by addition of two matrices, then you can distribute the multiplication over the addition like this. So c times a plus b will be equal to ca plus cb. Now if you want to see the proof of this, what is c times a plus b? Here a and b are matrices, right? So let's say a is an m cross n matrix, and if you have to add a and b also has to be an m cross n matrix, right? Orders must be same, and c is any scalar. Then for a plus b, the ijth element will look like aij plus bij, right? And when you are multiplying it by c, then the ijth element of this entire product will give you another matrix which is of order m cross n, and the ijth element will look like c times aij. You will just multiply c with this ijth element. The ijth element is aij plus bij. So ijth element will become c times aij plus bij, which is nothing but c times aij plus c times bij. This is the ijth element of this product. Now similarly, if you do the right hand side was c times a plus c times b. So here c times a will become an m cross n matrix, and c times b will also become an m cross n matrix, and the ijth element of c times a will be c times aij. We know this thing. And the ijth element of c times b will become c times bij. And these are two m cross n matrices which can be added, and the ijth element of the addition will again be c times aij plus c times bij, right? And this will also be an m cross n matrix. So both are m cross n matrices and the ijth term is exactly same. And hence, so what is the repercussion? Like we can say that, like let's say 3 times matrix A plus matrix B will be equal to 3 times A plus 3 times B. And same can be done for subtraction as well. If you have 3 times A minus B, that can be written as 3 times A minus 3 times B. So it is, scalar multiplication is distributive over addition as well, and scalar multiplication is distributive over subtraction as well. So this thing you can try to prove yourself, like just like this you can prove for subtraction as well, the exact same proof will be there. So the you can write it as c times A minus B will be equal to c times A minus c times B, okay. So this thing will also hold, and same thing for addition as well, okay. For addition we have already proved it, for subtraction you can prove it. Cool. So this is distribution. Now next is and like similarly you can write that scalar multiplication is distributive over subtraction as well, and we can write it here, c times A minus B will be equal to c times A minus c times B, okay. Now the next is, you can say that c plus d times A. So now if you have two scalars, So two scalars are added here, and times A can be written as C times A plus D times A as well. So you can say that like it is distributive both ways. Scalar multiplication is distributive over addition, matrix addition, and scalar multiplication is distributive over scalar addition as well. So we can prove this one also very easily. Okay, let's try to prove it. We have C times A, C plus D times A. Okay, C plus D is a scalar. Because C is a scalar, D is a scalar, you are adding two numbers, you will get another number. And A is a matrix, let's say of size m cross n, and the ijth element is Aij. So you are just multiplying C plus D to Aij. Okay, so the ijth element of this will be, so this will be another m cross n matrix whose ijth element will be C plus D times Aij. Okay, this is the ijth element, and which is nothing but C times Aij plus D times Aij. It is an m cross n matrix whose ijth element will be this. Okay, and same thing if you see RHS, RHS was what? C times A plus D times A. Okay, so here the ijth element of this A is an m cross n matrix, so C times A will also be an m cross n matrix. Similarly, D times A will also be an m cross n matrix. The ijth term here will be C times Aij, and the ijth term here will be D times Aij, and both will be m cross n matrices. Now since both are m cross n matrices, they can be added, they like addition criteria is satisfied, and this will give you an m cross n matrix whose ijth term will be C times Aij plus D times Aij. So both will have the same terms in all the rows and columns. So both of these are same matrices, and hence you can say that C plus D times A is also equal to CA plus DA. Similarly, you can write it for subtraction as well. You can say that C minus D times A is equal to C times A minus D times A. You can prove it just like as we did for addition. For subtraction also you can prove it. This theorem also holds. Okay. So let me write it here. You can say that C minus D, C minus D times A is CA minus DA. Always remember here capital letters denote matrices and small letters are denoting scalars. Okay, cool. Now next is associativity with scalars. You can have AB times A is equal to A times BA is equal to B times AA. So you can multiply them in any order. Okay, again it's a very simple theorem, simple property to prove. So if you want to prove it, it is saying that if you have AB times A, now here A and B are scalars. So A into B is also a scalar, and A is a, let's say, m cross n matrix whose ijth term is Aij, and AB is a multiplication, like it's a number. So AB times A will also give you an m cross n matrix whose ijth term will be AB times Aij. It is an m cross n matrix. Now if you do A times B times A, which means you are firstly multiplying the matrix by B and then you are multiplying A, then also same thing will happen. Here the ijth term will become B times Aij, and it is also an m cross n matrix. Then you are multiplying A to it, that will give you again AB times Aij as the ijth element, which is essentially the same. And same you can do like for B, you can multiply B later and multiply A first. It doesn't matter. Here also at the end you will get A times B times Aij as an m cross n matrix. Okay, so it doesn't matter, the order doesn't matter, all three will give you the same matrix at the end. So this property also holds. Okay, so you can say that with the scalars we have associativity, which means when you are multiplying two scalars and a matrix, the order doesn't matter, you can multiply them in any order, you will get the same result. Next is identity element. Okay, so 1 is the identity element, 1 as a scalar. This is not a matrix, this is the scalar 1 here. The scalar value 1 is called the identity element for any matrix. Now what is identity element? It is the number which you multiply with any matrix such that you will get the same matrix. So if you multiply any matrix by 1, you will get the same matrix, and hence 1 is the identity element for any matrix. It is very simple, we don't need to prove it, right? You are just multiplying 1 with every value, you will get the same values back, essentially you will get the same matrix back, and hence 1 is the identity element for any matrix, okay? So these are some of the properties of matrix addition, matrix subtraction, and scalar multiplication. Okay, here we can see a real life example of how scalar multiplication is used. I told you in the first lecture that matrices are used to represent grayscale images, which means images which only have black and white colors. So in a matrix, I can just write the grayness essentially. 0 means completely black, 255 means completely white, and any value in between will tell you how gray that particular pixel is. For example, here it is an image consisting of how many pixels? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 and so on. We have 25 pixels, right? It is a 5 cross 5 grid. It is a 5 cross 5 grid. So you can represent this entire image in a 5 cross 5 matrix, which will contain just the like the values, like how much gray every pixel is. So for example, let's say this is completely black. This does not look completely black, but let's say this is completely black, so this will become 0, and let's say this is like somewhere halfway around white. So let's say it's 120, okay, and you have some values, it's a 5 cross 5 matrix. Now if you do a scalar multiplication on this image, let's say I multiply this image by 1.5, then all the values will be multiplied by 1.5, 0 will remain 0, so black will remain black only. But all other pixels will intensify, they will become more white, right, because 120 will become 180, so now it will become more white. So you can use scalar multiplications to brighten the image, It works with RGB as well. Even if the image is colored, when you adjust the brightness of an image on your phone, it is doing nothing but essentially multiplying the red, green and blue component of your image by a certain value, and hence it will look more bright. So here this image is actually brightened, it's like 1.5x. So here the factor used is 1.5x, which means every pixel value is multiplied by 1.5, and hence you see the image is slightly brightened, okay. And same you can do with colored images as well. So this is a real life application of how scalar multiplications actually help brightening the images, okay. Cool. So this was all about the properties. Now let's look at some examples. Here we have two matrices A and B. A is a matrix of size or order 2 cross 2. B is also a matrix of order 2 cross 2. Both are square matrices. Now we have to compute A plus B. So A is 2 minus 1, 0, 3 and B is 1, 4 minus 2, 5. We can directly do this. A plus B will be what? It is just element by element addition. So here you will have 2 plus 1, which is 3. Then here you will have 0 minus 2, which is minus 2. Then you will have minus 1 plus 4, which is 3. And then 3 plus 5, which is 8. So element by element addition I did, and this is what I will get as A plus B. It will also be a 2 cross 2 matrix. And since the order were same, they are like you can add them. If the orders were different, you cannot add them. Next is 2A minus 3B. 2A minus 3B. So firstly you will have to compute 2A. 2A is a matrix where every element is multiplied by 2. So it will become 4, 0, minus 2 and 6. Every value is multiplied by 2. And then you have minus 3B. So minus, let's compute 3B. 3B means every value is multiplied by 3. So you will have 3 1s are 3, 3 4s are 12. Then 3 times minus 2 is minus 6. 3 times 5 is 15. Now we have to subtract these two matrices, matrix A minus matrix B. Again the order of both of them are same, and hence we can subtract them. So we will get a matrix 4 minus 3 is 1, minus 2 minus 12 is minus 14, then 0 minus minus 6 means 6, and then 6 minus 15 means minus 9. So this is the matrix you will get, okay, when you do 2A minus 3B. This is the second part. Now coming to the third part, we have 7 times A minus I. 7 times A minus I. Now I by default means identity matrix, okay, and here A is a 2 cross 2 matrix, and we know that identity matrix is always a square matrix which has diagonal elements as 1 and non-diagonal elements as 0. So they have not said what is the size of the identity matrix. Okay. So we have to perform this subtraction. We can only perform this subtraction if identity matrix is also of the same order of A. So here it is not mentioned like I is what, but you have to assume that I is by default denotes identity matrix in linear algebra. And like what will be the order, because A is of order 2 cross 2, I also has to be the order 2 cross 2. So they are talking about an identity, like here I means an identity matrix of size 2 cross 2, which means 1 0 0 1. This is the identity matrix of size 2, right? 2 cross 2. We know this thing. So we will compute 7 times A minus I. So firstly let's compute A minus I. A minus I is what? A is this matrix, I is this matrix, 2 minus 1 is 1. Minus 1 minus 0 is minus 1, then 0 minus 0 is 0, then 3 minus 1 is 2, right? This is A minus I, and hence you have to compute 7 times A minus I means 7 times this matrix, which is nothing but 7 ones are 7, 7 into 0 0, 7 into minus 1 minus 7, and 7 into 2 14. This is the matrix. Okay, this is your answer. So final answer is also a 2 cross 2 matrix. So this is the answer of third part, this is the answer of second part, and this is the answer of first part. Okay, this is how we solved all the 3 parts in this problem. Cool. Let's move to the next question. True or false? You have to just say that these statements are true or false. First is matrix addition is always defined for any 2 matrices. Is the matrix addition defined for any 2 matrices? False, right? No. Reason being, they have to pass certain properties, like there was a criteria. It is not for any 2 matrices, it is for only matrices having the same order. If the order is same, then only matrix addition or even subtraction is defined. So this statement is false, it is not defined for any 2 matrices, it is defined only if for the matrices which have the same order. Now moving on to the second statement, 2 times A plus B is equal to 2A plus 2B, this we have already seen. Scalar multiplication is distributive over addition, and hence 2 times A plus B will be equal to 2A plus 2B, this is true. Okay, we have already seen this property. A plus B is equal to B plus A for all matrices of same order, which means matrix addition is possible, then A plus B will be equal to B plus A, this is also true, this is nothing but the commutative property of addition. Okay, so this is distributive property, and this is the commutative property of addition. Okay. Next is A minus B is equal to B minus A for all matrices of same order. This is incorrect. We know that subtraction is not commutative. Subtraction is not commutative. In fact, now I can write a rule. In fact, now I can write a beautiful rule. I can say that A minus B is equal to minus 1 times B minus A. Minus 1 is a scalar multiplication here. Or we can also write it this way. We can say that A minus B is equal to minus of B minus A. Whenever you have minus of something, it is nothing but minus 1 into, right? Just like our numbers, okay? Just like our integers or numbers, like same thing happens here. I can write that A minus B is equal to minus of B minus A or minus 1 times B minus A, right? They are not equal, actually they differ by a negative sign, because like every number has to be multiplied by minus 1. We have seen an example as well. Every number was differing in the sign, and this can be very easily proved. The ijth element of A minus B will be Aij minus Bij, M cross N matrix. Let's say A is an M cross N matrix with ijth element as Aij, and B is an M cross N matrix with ijth element as Bij. Then for A minus B it will be Aij minus Bij. Now same thing for B minus A, it will be the ijth element will be Bij minus Aij, M cross N matrix, and you are multiplying it with minus 1. So the ijth element will become minus 1 into Bij minus Aij, which is nothing but Aij minus Bij, right? M cross N matrix. So now these two have become same. So for matrix subtraction, A minus B is nothing but minus 1 times B minus A. Every element should be multiplied by minus 1. and it is not commutative. It is not commutative, and hence the fourth statement here was false. Okay, matrix subtraction is not commutative. Cool. So these were some examples on matrix addition, subtraction and scalar multiplication. We saw some properties. In the next lecture, we will see some more operations on matrices, specifically matrix multiplication, which is one of the most important operation on matrices. So thanks for watching this lecture. Let's meet in the next lecture. Bye bye.